Okay, so today's lab is on capacitors. I will pull up the Canvas screen. Okay, so we have these instructions. Um, the lab's worth 55 points, much less than some previous labs. I think this is a relatively short lab. Once we get into the instructions, we'll see this. Let me go up to the top. So just like normal, we have um, sort of a introduction section with our um, equations that we might end up using just a little bit. I don't think there's too many calculations in today's lab. Um, but remember at the top, always include your own introduction somewhere near the top up here. Once we get into the simulation, it's this right here, is at PhET. Let me pull those up. You're going to see something like this. And for the first, I think maybe two parts, we're going to do just this capacitance section right here. Click on this, and similar tools from the previous couple labs. It's a bit different though. We have a way to measure voltage. We should know how to do that by now. We need to measure across something. So let me um, describe. This is the capacitor right in the middle, these two large plates that are separated by some distance. The distance separation is right here, and the area of the individual plate is right here. And measuring voltage, I would measure across the object I want to measure. So for this element, the capacitor, I measure across. So on both sides, you see the potential difference from one side to the other. Okay. In here, you can play around with this for a bit, but once you get started, you'll follow the directions. You could increase the voltage of the battery. Actually, first, let me reset. So the important things to make sure that are checked off, all four boxes are checked off in the top right. So you see plate charges, bar graphs, and electric field, and current direction. Okay, now we could get started. I can manipulate the voltage of the battery, sliding this dial, this lever, and it's mainly a qualitative lab today. So let's go into the instructions. It'll be like, um, we could only measure voltage. So um, measuring that, observing what happens to the arrows, stuff like that. Qualitative uh, directions for most of it. Once we get down into, I believe, part two, um, right here. So we will charge the capacitor. So we will supply some charge to it. This is arbitrary. I'm just doing an example. And we will disconnect it from the battery. And you will use these dots up here um, to disconnect the capacitor while it is charged from the battery. And that will be mainly used for the next section. Let's go on to that. So after we get through that, observations and measurements, then we'll go into a different section where we're going to be um, hooking up a light bulb. So that's part three. Let's go to that. What you can do, you can refresh the whole page, the top left, or you could just hit the light bulb button down here. And now we have this arrangement. Okay, so similar to hooking up, uh, step by step, telling you what to hook up to the circuit, and it should be fairly easy. Um, let's see, I'll do an example one. So we'll see how, I'll just do very little. Make sure all the boxes are checked like this. And we see how the capacitor will discharge by going through the light bulb. You can describe, is something brighter, less bright, uh, things like that for whatever it asks. At the bottom, I know there are quite a few people who stick around for the whole time. I'm going to say for this bottom section, it says a challenge right here. If you ask questions down at this bottom section, I might be a bit more vague than you're used to. So I'll keep this to, you trying your best to see what you think down here for, part 4. Okay, and at the bottom, conclusion, you can fill out this survey to see how the instructions, or give your input on how the instructions are written. Okay, so we have, remember, always include your conclusion at the bottom, and always have your own introduction somewhere near the top. All right. Any questions about the procedure or these instructions? Okay. Let's see. I don't think I'm going to have like a thing to check off today. I'm just going to say, I'll have people stay to watch the notes. I will say though, this is a short lab, and if you do stay, you can probably finish it in under an hour. So that's maybe motivation. You could get it finished today and right now. Okay, let me go over the notes real quick. Right. This one. All right. Capacitors. What is a capacitor? Oh, I had a thing. A capacitor is just a piece of metal, a piece of two sort of slivers of metal. They could be slivers or discs or whatever. And they are sort of rolled up into a little ball. And commonly in a circuit, they might look something like this. So you might see something like this. Now imagine this is sort of like two thin pieces of metal rolled up, and they're separated by a piece of paper that keeps them. Oh, here, look at this. They are separated by a thin piece of paper or a different type of material so that the two sides don't touch. Let me do it. Let me put that over here. Let me put the diagram symbol for it. So capacitor is just two plates like this. And actually I want to have these be sort of rectangles. No, I could have them like this. Let's hook it up to a battery. Battery is like this. That. Like that. Okay. Now, before I hook it up to the battery, let me let me disconnect it. And these are two pieces of metal that are neutrally charged. They have equal numbers of positive and negative charge on top of them. So, um, what I was going to do, I was going to have these as like bricks like that to show that they are physical pieces of metal. But I'm just going to have them. I'm just going to use this diagram. So they have positive and negative an equal number of positive and negative charges on both sides. So they're neutral. Then, once you hook this up to a battery, now let me connect it to the battery. Now, there is this freedom for the charge to move somewhere. Um, First, I could do this. Let me put down here. I put it down here. Um, it's a lie. I'll put it up here. Capacitors store charge. I just wanted to have that somewhere before I get started. Okay, so now we hooked it up to this battery. What's going to happen? Um, Typically, in most of the labs up to this point, maybe even your lecture instructor has gone over this. There is commonly we would think there's a current that comes out of the positive side and goes that way and goes up and through whatever part of the circuit that we're talking about. However, this has been sort of the big lie of the semester. Um, what we call this current that's flowing this way, we've been calling it positive, this positive flow of current. If you have seen in a lot of places on these labs, there's the electron version of the circuit, and there's the conventional current version of the circuit. So what's actually happening when we say that there's a current flowing in this circuit, let me do just a very basic circuit up here that we've seen before. Positive, like this. So I previously said the current flows that way and then through and then all the way back. What's actually happening, and I may have labeled these positive. A positive current flowing this way. What's actually happening, now that we are more familiar with, currents flowing through a circuit, what's actually happening is there's this flow of electrons that isn't going this way. It's going the other way. And it wasn't until um, physicists learned more about um, electricity and circuits that we figured out that it was the electrons that are the ones that are moving. So the electrons moving, not the protons. So if we look at the material of this uh, capacitor, these pieces of metal, There, I'll make them little thin pieces of metal like this. These little thin pieces of metal have protons and electrons. Those are the things that, are charged. The protons can't move. It's only the electrons that are moving. So what's going to happen? The negative charges, the electrons, once they're connected to this battery, they're going to be attracted to this large positive plate. They come out down the wire and go towards the towards the positive plate, like this. That's that. And similarly, as one electron reaches the plate, we have one electron over here that wants to get away from the negative side of the battery, and it will go that way, and it will go that way, and it will go towards that plate. There we go. Now, after some time, let me make it again. After some time, there'll be slightly more positive charges on one plate and slightly more negative charges on the other. And this is because the negative charges are slowly moving in this way. And it isn't until, do one more. It isn't until there are so many positive charges on this right side plate that the electron that was traveling in those previous two pictures, the electron gets to this point right here in the middle and is both equally attracted to the plate up there and to the battery down there. And so that's when this flow stops and it becomes stable. But at this point, you see there is this slow building up of charge, or this slow sort of separation of charge between these two plates. Okay. Let's see. Specifically, maybe we could do, yeah, we could do that. By the way, the person, so we had this, I may have said this in this class already, but there was conventional current that goes this way, but actually this is the real scenario over here. The person who got this mistake wrong or made it confusing like this was Benjamin Franklin. He's the one who decided that there's a positive current and it goes that way. But at that time, electricity wasn't as well understood. It wasn't until much later when we knew what electrons were, where we figured out this was wrong and it was this over here. Anyway, now we have this capacitor up here at the top. Capacitor that holds a specific amount of charge. So let's look at the charge. There's a certain amount of charge on each plate. Let's see, did I do it right? I did. No, I need to add one more. There. So if there was positive 6 coulombs of charge on one plate, there is an equal amount on the negative plate. There's a negative 6 coulombs on the negative plate. Okay, that's the charge. Charge is commonly Q. And from, I believe, the second or third lab, we know that if there's a collection of charges somewhere, there's going to be a potential difference. So since these two plates have a lot of charge in one space for each of them, there's going to be this potential difference between the two. Let me I'll just put this over here, -6. Okay. And it is a combination of the potential difference and how much charge could fit on a plate that determines a capacitor's capacitance, C. So it is one way to determine. Let's write the equation out. So capacitance, C, is no, we'll start with this. The typical formula, the formula that's in the lab instruction, is Q equals C times V. So that's the amount of charge on one plate. On one plate. C, so charge. The C that's capacitance. V is voltage or potential difference. Okay, so we can rearrange this formula, put it over here, because we're focused on capacitance today. So the capacitance of a capacitor. C, let's solve for C. That's just the amount of charge over the potential difference between the two plates. Okay. The units for capacitance, well, let's look at the units for each of these. We should know these by now. The units for a charge is coulombs. Coulomb. And V, that's just volt. And a coulomb per volt is a farad. That's the unit for capacitance. Okay. Let's see. All right. One more little picture. One more set of pictures, actually. So we have this battery. And I'm going to do like a 3D sort of picture of these two plates. That's, let me make that better. Okay. Okay. So we have this capacitor. This is just a 3D picture of it, and there's this voltage difference between the two plates. That voltage difference, or at least I should say, that voltage difference between the two plates is the same as the voltage supplied by the battery. Um, Now, capacitors can be different. So say I take this battery for um, this system, this sort of large capacitor, and I put it on some smaller capacitors like this. So that's the same exact battery, but the capacitors are different. It makes sense, visually, that these capacitors over here on the left can hold more charge and have a much bigger capacitance than these over here. So that could only hold so much, even with the same battery over here on both of them. So we might be tempted to say, let's go Q over V. So we might be tempted to say that as the amount of charge increase on the capacitor, the capacitance gets bigger and they're directly related. That's not the case. No. What's actually happening, we need to let me write this. Let me put, no. What's actually happening is that as the charge increases, the amount of voltage across the two remains the same. That also increases. Let me go like this. Put that over there. Because I just said a moment ago, the voltage between the two remains the same as the battery that's provided. So there's this relationship that keeps this ratio the same. Typically, more directly, if we want to have this capacitance be different, we need to physically get a bigger capacitor. And to do that, that's given as our other equation. What was it? It was E naught. No, it was kappa E naught A over D. So there are these two constants right here that um, we're not going to, be investigating too much in the lab. You just think of these as how easily something can hold charge. How does the material uh, do when holding charge? How well can it hold it? The other factors in here, A, that's the area. How big are these capacitors? And D, that's the distance between them. Between them. Okay, so in order to get a larger capacitance, we would need to have a differently shaped or differently arranged capacitor. Okay, so somewhat a lot going on, but not too bad. That. Okay, I think that's it. Are there any questions with this? Okay. Let me make the breakout rooms, and I'm going to say that right. So I'm not checking anything off today. It's a very qualitative lab. Um, and if you do have questions or you want to, talk to me, I'll be here in the main room. And yeah, so that, and the rooms are open.